Welcome back to your last lecture of the second to last week of new material. This is Physics 235, week 13, day 3, scheduled for release on April 17th. And today we're going to be talking about the double slit experiment and the idea of interference. So there's a very famous experiment in physics known as Young's double slit experiment, where Young is some figure from the history of physics who I don't need you to know anything about. But Young made a very important discovery that finally helped to convince the scientific community of something. Newton had been very adamant that light was a particle, and despite other scientists claiming that light was a wave, Newton was such a powerful figure in the scientific community that most scientists accepted that light was a particle. It was Young's double slit experiment that finally proved to scientists that light had a wave nature. And before we explore this, I want to return to the idea of interference. First, I want to put on the board a source of waves, or a source of wavelets. You could think of this as something small bobbing up and down on the surface of a pool, creating water waves, if you want a physical analog. So this is an example of what the wave fronts might look like for a single point source of waves. If we're talking about sound waves or light waves, these will actually spread out in spheres, but we're drawing them on a two-dimensional surface, so we are left with being able to draw circles. This is slightly different than the other diagrams like this I've showed you, because here I've labeled both the crests and the troughs of the waves, where the thicker lines that are solid are the crests of the waves, and the thinner dotted lines are the troughs. And when we have two different sources of waves at different locations, those waves will combine to make an interference pattern. So let me add a second source of waves here. So I've now added a second source of waves here with its own wavefronts moving outward, and these two wavefronts are going to overlap with each other and create what's called an interference pattern. And let's look at this and see if we can figure out what this interference pattern might look like. For example, see if you can find some locations where you would have constructive interference. I'm going to give you guys maybe 5 seconds to pause the video and think about this yourself, and then I'll show you the answer. So constructive interference happens when the crest of one wave lines up with the crest of another wave, or where the trough of one wave aligns with the trough of another wave. So we now just need to look at our diagram and figure out what locations would allow this to happen. Well, a crest lines up with another crest where we have two solid lines crossing. So I'm not going to label all of these points, but some of the points where crests line up with crests, I'm going to label here in red. But you could also have a trough lining up with another trough. So there are some additional locations I could label here that will still be constructive interference that I'm about to label in red again. So in terms of this diagram, anytime we have a solid line crossing a solid line or a dotted line crossing a dotted line, those locations are constructive interference. Destructive interference, on the other hand, is where the crest of one wave lines up with the trough of the other. So what we're going to be looking for here is where a crest lines up with a trough, or where a dotted line intersects a solid line. So let me label those locations in this area we've been labeling things. So all of the points I've labeled in green are points of total destructive interference. So if we were to let this image play, we would see at the red points the waves oscillating up and down with maximum amplitude, an amplitude equal to twice the amplitude of either individual source. And at the locations of the green dots, we would see zero amplitude. The water, if this were a water wave, would be not oscillating at all at that point, and the surface of the water would remain still as everything else around it oscillates. And this is called an interference pattern. And interference patterns only happen with waves. So if we can find some way to create an interference pattern using light, then we know that light must act like a wave at least some of the time, and this is what Young did. One thing I do want to remind you of very quickly is the idea of coherent sources. We're going to be assuming the sources in all of the things we talk about today are coherent, meaning that both sources are at a crest at the same time and at a trough at the same time. We can see this in the diagram by looking at the center where the sources are. So I'm labeling the sources in orange here at the center of these concentric circles. And the crests and troughs are evenly spaced. So for the source on the left, if this circle that I'm outlining in orange is a crest, and the dotted line circle a little further in is a trough, that must mean this source is at a crest at the moment displayed in this image. And if we look at the other source, we see the same thing. If this solid line is a crest and the dotted line further in is a trough, then the source itself at the center must be at a crest at this moment. So since both sources are at a crest at the same time, these must be called coherent sources. We'll also be able to see the features of this interference pattern by bringing back the idea of a path length difference. So if we looked at the path to this point of constructive interference right here, well, it took light from this source this distance to reach that point, which if we're counting wavelengths starting at the source is 1 wavelength, 2 wavelength, 3 wavelengths, 4 wavelengths. So this source took 4 wavelengths to get to this point, while the other source followed this path to get to that point, passing through 1, 2, 3, 4, 5, 6 wavelengths to get there. So one source took 4 wavelengths to reach this point, the other source took 6 wavelengths to reach this point, so we say the path length difference is 2 wavelengths. And if you think back to what we talked about with sound, when the path length difference is a whole number multiple of the wavelength, you get constructive interference. And correspondingly, when the path length difference is a half wavelength, 1.5, 2.5, 3.5 wavelengths, you will get complete destructive interference. Just a note here that m does have to be an integer for any of these equations to work. So I reminded you or let you know earlier in the term that we were going to return to this idea of path length difference, and the next few lectures, the idea of a path length difference will be incredibly important. So now that we have some of the basic ideas and terminology defined, I want to show you the experimental setup that Young used for his experiment. So this is the experimental setup for Young's double slit experiment. We have 3 screens here. The first screen here has a single long narrow slit cut into it. The second screen has 2 long narrow slits cut into it, separated by a distance d. And the third screen here is the viewing screen. This is where the light is going to be cast onto this screen, and we will see the pattern with a distance of capital D separating the screen with 2 slits from the viewing screen. Now first, Young shined monochromatic light onto the first screen with the single slit. Monochromatic light just means there is only a single wavelength involved. Then, that light passes through the first slit and spreads out. And we know from our lecture on Huygens principle that light spreads out like this because of a process called dispersion. Remember that dispersion only happens if the wavelength of the light is roughly similar to the size of the opening. So if that slit were too large, we would not have a lot of diffraction happening. Or, sorry, would not have a lot of dispersion happening. So now the light that's dispersing out of slit S0, labeled right here, that light is going to fall on these other two slits right there, meaning light will then disperse out of each of these slits, out of the top slit and out of the bottom slit, creating that interference pattern similar to the one we saw on the previous page. It's worth mentioning that we know for sure that the light coming out of slit 1 and the light coming out of slit 2 are going to be coherent. And that's because the source of the light for both slit 1 and slit 2 is this monochromatic light we started with. So the only light source we have is whatever's producing this monochromatic light, most likely a laser. So as long as S0 is at a height that is directly in between S1 and S2, the light will travel the same distance from S0 to S1 as it travels from S0 to S2 here. Which means that S1 and S2 will have light coming out of them that are both at crests at the same time or both at troughs at the same time. This means that slit 1 and slit 2 will produce coherent waves. They will both be at crests at the same time or both be at troughs at the same time, which will be important for a lot of the math we do later in this lecture. Then, at the end of this whole thing, we see a pattern of light and dark fringes on the viewing screen over here at the right. This is as though we took our image from the previous page and just drew a horizontal line across it some distance above the two sources. Since we're using slits here, these wave fronts that are spreading out in between our screens are actually going to be more cylindrically shaped than spherically shaped, so we get lines rather than individual points, but we do get an interference pattern, an alternating series of bright and dark spots, which can only be explained by constructive and destructive interference, which is a wave phenomenon. So to show you this same idea from a slightly different angle, I want to put a different diagram on our screen right now. What you see now is more of a physics-oriented diagram, a diagram that will help to explain the physics of what's happening rather than demonstrating the actual equipment used to make these interference patterns. So we have our monochromatic light coming in over here, and we can see the wave fronts are parallel, and then we have each of our two sources, source 1 and source 2, each with their own interference patterns spreading out, where again, these solid lines are crests and the dotted lines are troughs. So again, let's label some points of constructive and destructive interference. So I haven't labeled all of them, but you can see some points of constructive interference I've labeled in red, just like we did on our original diagram. And it will turn out that if you draw a line connecting all of these points, every point on that line will also be constructive interference. So drawing a line connecting these lower series of dots will all be at constructive interference at all points along those lines, creating a maxima. Or for this other set of red dots I drew, every point along this line that connects them will all be at constructive interference, creating a maximum of brightness. And correspondingly for destructive interference, all of the points I've labeled in green have destructive interference. So if we connect these points in a line, every point along this green line I just drew will be at destructive interference, which will produce a minimum of brightness. The same idea happens along this other set of green lines, will also produce a minimum of brightness. So on the screen over here that I've labeled with the blue arrow, we will see an alternating pattern of bright spots and dark spots. And you can see a picture of what this might look like over here in the location I've labeled with the purple arrow. And in this section right here especially, you can see that we have a bright spot and then a dark spot and then a bright spot and then a dark spot. And all the points I'm labeling with these purple lines are all bright spots with dark spots in between them. Now this pattern that you see on the far right in the black bar is not the pattern that matches with the actual interference pattern we have shown in the diagram in part A of this figure. So if we wanted to label the bright spots, we would have a bright spot here where the maximum is, and then a dark spot where the minimum is, and a bright spot here where the maximum is, and then a dark spot where the minimum is. And then there would be another bright spot out here, and so on, continuing down on the other side. Now these little bright and dark spots I've labeled in purple right now are not perfectly evenly spaced, and that has to do with the scale at which our diagram is drawn. On this scale, it looks like little d, the distance between the slits, is almost as big, maybe about a third as big, as the distance from the slits to the viewing screen. But in reality, little d is going to be much, much smaller than big D. It will turn out changing the distance between the slits will spread out or condense our pattern of bright and dark fringes in a way that I'll show you by means of a GIF a little later in this lecture. The only other thing I want to point out is that some of you might be asking yourself, hey Brendan, what about these spots here? I see that we have alternating bright and dark spots, and they slowly get dimmer as you get further out to the side because dispersion is strongest in the center and gets weaker as you go to the edges. But what about these extra dark spots that I've labeled in yellow? And my answer to this question is, congratulations for noticing something like that. You have very good observational skills. Also, I'm going to have to put off answering your question until we talk about the single slit interference pattern. And this pattern of bright and dark spots can once again be explained by the path length difference, or the extra distance traveled by one slit versus the other, and we're taking the absolute value of it because -1 wavelength and +1 wavelength will both give you constructive interference if that's your path length difference. But if we look at this maxima right here, or this maxima here in the center, let's start with the one in the center, we would have a distance L1 traveled by the light from slit 1 to reach that point, and a distance of L2 traveled by the light from slit 2 to reach that point. And since that maxima is directly in the center of the two slits, we would have L1 minus L2 gives us a value of 0 for the location I've labeled and drawn my distances in blue. Let me make those a little darker since this is a pretty busy diagram. And this fits nicely with our understanding that constructive interference happens when delta L is equal to a whole number of wavelengths, where again, m has to be an integer. And then if we look at the next bright spot, and I'm going to label this one in purple instead, this bright spot here, L1 would be this distance, the distance traveled by light from slit 1 to reach this particular point on the screen. And the distance traveled by the light from slit 2 to reach that point on the screen is going to be, again, L2, where I'm labeling these in purple to distinguish them from the values in blue. So here, if we take the difference between L1 and L2, or the absolute value of it, since this is the next maxima over, we are going to know for sure that this difference is 1 wavelength. And the next maxima over would have a path length difference of 2 wavelengths. And the next maxima over would have a path length difference of 3 wavelengths. So, think for a second, what do you think the path length difference is for this minimum that I've circled very boldly in green? And the answer is that the path length difference there will be half of a wavelength. And if we go on to the next minima along, then our path length difference will be 1.5 wavelengths. And we're going to use a number called m to refer to these different maxima and minima. And let me clear off a little room here so that I can draw this a little more clearly. Our maxima will be labeled with m values. So this central maxima will correspond to m equals 0. And the maxima on either side of this will correspond to m equals 1. And the next one would be m equals 2. So completing our path length difference formulas up here, the path length difference for destructive interference is a half integer number of wavelengths, where again, m has to be an integer. M is also called the order of the fringe by some people. So, for us to be able to attack a problem like this mathematically, we're going to need to know some way of determining the path length difference. And that path length difference should depend on some of the features of our system, possibly the distance between the two slits, possibly this distance from the slits to the screen, big D. And I want to show you a diagram to help explain that. And before I show you that diagram, I want to remind you that this diagram we've been looking at is not to scale. In reality, big D, the distance between the slits and the screen, is much, much bigger than little d, the distance between the slits. So, with that in mind, let me show you the following diagrams. Here we have on the left a similar diagram to what we've been looking at so far. We still have our two slits here separated by distance d, and the light is going to travel along two different lengths, R1 from slit 1 and R2 from slit 2 to reach some point P on the screen. We're going to say that this point P is a distance y from the center, and the angle between the line sticking straight out from the center of the slits and a line that goes from the center of the slits to point P, that angle is going to be theta. But just a reminder, this diagram on the left is like our other diagrams. This is not to scale, because we know that big D is much, much bigger than little d. So here we have the diagram on the right to clarify this. Little d, the distance between the slits, will be fractions of a millimeter. So we're talking about like 0.1 millimeters, maybe even smaller than that. But the distance to the screen, big D here, is going to be more than a meter. So we have a big D that is at least 1,000 times bigger than our little d. So if we make our diagram to scale, we're going to see that when the rays exit the slits, that they are effectively parallel to each other. Let me draw something just to try to make that clear. So if we're trying to draw this to scale, then we might have something like this with the screen over here. And right in there, those two tiny little dots, or the two tiny little gaps in the line, are the slits. So if we follow the path of light from the top slit to the screen, and we follow the path of light from the bottom slit to the screen, you can see that those light rays are very, very, very close to parallel. And they're so close to parallel that we are going to assume that they are parallel. So that means these two rays, to use the same colors as before, this red ray right here and the green ray below it, are effectively parallel to each other. And we're going to assume that they actually are parallel to each other. So what this means is that if we draw a blue line right here through our diagram, the distance that these rays of light travel after they pass this blue line is going to be the same on their way to point P. This means that the part of the green ray that is to the left of the blue line is going to represent the extra distance traveled by the green ray in this case. Or, in other words, this distance that I'm about to label in purple is the path length difference. I've sometimes labeled these distances L1 and R1 from slit 1 and slit 2 respectively to point P, and sometimes I've labeled them as L1 and L2. So R1, R2, L1, L2, they represent the same thing. Your book is calling the path length difference delta L here, so I'm going to stick with that. So we want to see if we can find some sort of mathematical expression for that side, or that extra distance that the green ray travels. And there's a triangle here that we can make use of that I'm going to outline in yellow. So one side, the hypotenuse, is the distance between the slits. One of the sides of the triangle is there, and the last side of the triangle is along this green ray. So we have a right angle right here, and we already said that the angle theta is the angle between the center point of the slits and point P, and the center point of the slits going straight across. But if our light rays are effectively parallel, then that means this angle theta is the same as this angle theta, which means this angle that I'm labeling as phi has to be 90 minus theta, which means that the angle inside of our triangle also has to be theta. So all of these angles I've labeled as theta in pink are the same, and the angle that I labeled as phi is 90 minus theta. So we have ourselves a right triangle here, and we can do a little bit of trigonometry. So we want to know the path length difference, which is the opposite side of the triangle from that angle theta, and we know little d, the distance between the slits, which is the hypotenuse of this triangle. So we need a sine of theta. So we can say that sine of theta equals the opposite side, which is our path length difference, delta L, divided by the hypotenuse, which is little d, the distance between the slits. So we can say that our path length difference is going to be equal to d times the sine of that angle theta. So make sure you study this page right here so you can see very clearly why this must be the case. The geometry of this problem is kind of done at this point, and we're about to jump into some more mathematical stuff and simplify our equation somewhat. And to do that, I'm going to clear some space on the left side of our screen over here. So to restate our rules for constructive and destructive interference, now that we know that the path length difference is equal to d sine theta, or at least approximately equal to the extent that our rays are actually parallel, we can say that constructive interference will happen when d sine of theta is equal to some whole number times the wavelength. And destructive interference happens when the path length difference d sine theta equals a half integer times the wavelength. So the next thing we're going to do here is apply something called the small angle approximation. When angles are small, less than about 15% for a 1% error, sine of theta is approximately the same thing as tangent of theta, which is approximately the same thing as theta, where theta, just as a reminder, must be in radians for this last step to be true. So that means we can rewrite sine of theta here as tangent of theta. Or at least we can write sine is approximately equal to tangent. And if we go back to our triangle, or rather to a different triangle, this triangle that I'm labeling in pink on the left side of the diagram. The theta in this triangle, down here, is the same as the theta in our yellow triangle to the right. So we know that the tangent of theta equals opposite over adjacent. Or in the case of our pink triangle, the opposite side is called y, and the adjacent side is big D, the distance from the slits to the screen. So y here is the distance from the center of the interference pattern to point P. So this means that we can write a couple more formulas here that I am going to write down in green to go with these two very important formulas in blue up here at the top. If you're going to box anything from today's lecture, box this equation, these equations right here, although I do expect you to be able to explain how we got to this point. So if we're dealing with small angles, then that means we can locate our bright fringes. And our bright fringes are going to be located at what we call y sub m, the bright fringe for the mth order maximum. So plugging in y over d for sine of theta, we get the following equations. Which means our bright fringes are located a distance of y sub m equals m times lambda times d divided by little d. This is another equation I would box for this lecture, and make sure you know what y represents here, and that it is just for bright fringes. If you want the corresponding formula for dark fringes, just replace the m with an m plus 1/2. And we can see here that we would expect our bright fringes to be equally spaced, because this equation is linear with respect to m. So if we double m, we double y. Eventually, this approximation will break down, and the bright fringes will no longer be equally spaced, and this will happen when the small angle approximation breaks down. So the only other thing I want to do today is an example problem. And that example problem is that we are going to shine green light, which has a wavelength of 540 nanometers, on two slits that are separated by 0.02 millimeters. I want you to find the distance between the first and fourth bright spots on a screen that is 1.8 meters away from the slits. And I want you to determine at what m value does the slit spacing stop being equal. And I also want you to determine how many bright spots are there, or in other words, what is the largest value of m possible. So we can see here that our little d is much, much smaller than our big D. So our small angle approximation is going to be valid. But before we get to actual calculations, let's just write down some of our known variables. We know that the wavelength is 540 nanometers, but we're going to need to convert that into meters. And a nanometer is times 10 to the negative 9th meters, so the wavelength is 540 times 10 to the negative 9th meters. The distance between the slits is given by little d, and little d is 0.02 millimeters. So we could write this as 0.02 times 10 to the negative 5 meters. Or if we wanted to, we could write this as 2 times 10 to the negative 7th meters. And the distance from the screen to the slits is big D, and that's 1.8, already in meters, so no need to convert. And for part A, we want to find the first and fourth order bright fringes and the distance between them. So on our screen here, we will have bright spots, and we'll have a bright spot for m equals 0, and m equals 1, 2, 3, and m equals 4. So if we can find y1, which is the distance from the central bright fringe to the first maximum, and if we can find y4, the distance from the central maximum to the fourth order bright fringe, we can find our answer here by subtracting the two of these. So we want to find y4 minus y1. We know from the previous slide that y sub m, when the small angle approximation is valid, is equal to m lambda d over little d. So we can say that y1 is equal to 1 times our wavelength, 540 times 10 to the negative 9th meters, times our big D, which is 1.8 meters, divided by our little d, which is 0.02 times 10 to the negative 3 meters. Oh, I made a mistake up above. Why didn't you guys correct me? How dare you? So this was millimeters. I combined the two versions of this number I was stating. That should be times 10 to the negative 3. If you wanted times 10 to the negative 5, that would be 2 times 10 to the negative 5. My apologies. And when you grind through these numbers, you get that y1 equals 0.049 meters. Then we can go through the same process for y4. Since they're evenly spaced, we could just take y1 and multiply it by 4, but let's go through the whole process. 4, the value for m, because this is the fourth order bright fringe, times the wavelength of 540 times 10 to the negative 9th meters, times the distance to the slits of 1.8 meters, distance to the screen of 1.8 meters, divided by the distance between the slits of 0.02 times 10 to the negative 3 meters, gives us a number that is 0.194 meters. And it turns out this is precisely, to within rounding error, 4 times our value for y1. So that means our answer is going to be y4 minus y1. So we get a distance between these two slits of 0.145 meters for part A. For part B, we want to know at what order do the bright fringes stop being equally spaced? Well, basically at what m do the fringes stop being equally spaced? So think about when do these fringes become unequally spaced? There was an approximation involved in saying that the fringes had equal spacing between them, and that was the small angle approximation. So the bright fringes stop being equally spaced when the small angle approximation breaks down. And this happens at around theta is equal to 15 degrees. So here we can use our other formula, that d sine theta equals m times lambda for a bright fringe, and plug in some values here. D is 0.02 times 10 to the negative 3 meters. We know our theta is around 15 degrees when the small angle approximation starts to break down, equals our value of m times our wavelength of 540 times 10 to the negative 9th meters. Be careful here that we have some units that are m. These stand for meters that I've circled in blue, but the m I'm circling in purple right now with an arrow above it, that is an actual variable, and that's the variable we're going to solve for here. And if you actually work through this, you get m equals 9.59, so our answer is around sometime between the 9th order fringe and the 10th order fringe. So if we took our answer to be the 9th order fringe, that means the central bright fringe and the next 9 on either side of it, making a total of 19, would all be about equally spaced, and past that point, the difference in the spacing would become more than about 1%. Lastly, we have the question of what is the largest order bright fringe possible? So, to answer this, we need to think about what it means to be at the largest m possible. Looking at the equation d sine of theta equals m lambda, we can see that our wavelength is going to stay the same no matter what value of m we have, and d is going to stay the same no matter what value of m we have. So as m goes up, so does sine of theta. But we have a maximum value of sine of theta. Sine of theta only keeps increasing as theta is increasing up to a certain point. After 90 degrees, sine of theta starts to go down as theta continues to go up. So sine of theta has a maximum value of 1 at 90 degrees. So we're going to use d sine theta in this case, where we plug in 1 for sine theta. So we have d, our 0.02 times 10 to the negative 3 meters, the distance between our slits, times our sine of theta, which has a maximum value of 1, equals m times our wavelength of 540 times 10 to the negative 9th meters. And again, note that in blue, these m's are units, and in purple with the arrow, this m is a variable that we're solving for. So, solving for m, we get an m value of 37.04, which means the 37th bright fringe is on the screen if we make the screen large enough, but the 38th bright fringe is not. That would be true even if this were 37.94. So for this type of question, you always have to round your answers down. So it is the 37th order bright fringe that is the last one that could be seen on the screen. And this would involve the light going almost perpendicularly out of the slits, so this would be a very, very dim fringe, and we would need an incredibly large screen in order to see it, but it is at least theoretically possible. That's everything I have for you today. Thank you for watching, and have a nice day.